Okay, I thought something like this would happen eventually. When it comes to AI, there's so much misuse of it, and it's horrible, and it's used for art as well. It's robbing people of such appreciation of their work and so on. There is all that. But there's, like any technology we create, we always misuse it. Every single time I look at the internet, it was a perfect example. It was like so-called social networks became unsocial networks and encouraged unsocial behavior, really. Yeah, they really did. It's ironic. Promised to encourage and improve your social life, and then just encourages those who are socially dysfunctional to get addicted to click, 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 selfie, selfie, and a bunch of other things that just don't equate to good social skills. Didn't improve a damn thing for them. So, scientists claim AI breakthrough to generate boundless clean fusion energy. Now we're talking. So that's a requirement, right? That's priorities. So at Vice.com, Vice is a fascinating group. Don't agree with everything they've done. It's just some interviews and some things they put out seems to be a bias in some ways. Other things are really in depth and informative. So depends what journalists they get on a particular team as well. So Vice, there are many stumbling blocks, it says on this article, on the racetrack to nuclear fusion. The reaction at the core of the sun that combines atoms to make energy, generating more energy than it takes to power the reactors, develop reactor-proof building materials, keeping the reactor free from impurities, and retraining that fuel within it, to name a few. I'd like to add, yes, it is impossible to break the laws of thermodynamics. You get out what's put in. However, over unity is a thing in terms of the cost of energy put into something by human intervention, and the rest of it coming out from just the way things are. Growing fruits and veg in your garden. You dig the ground, and hopefully it's fairly good quality soil. That's nutrients that will feed your plants. Sunlight is whole photosynthesis is energy. We don't need human beings to switch the sunlight on. Rain, watering the plants, sunlight. Bees pollinating flowers. Occasionally you might add more water, depending on what you're growing. And that's human intervention, clean water and whatever. But the point is that there's a whole plethora of things that go on with growing something in the back garden, that the energy and that comes from that for it to exist, majority of it doesn't come from human intervention. That's over unity. It costs less energy to put into something than what you get out. One seed for a runner bean plant produces several pods with way more seeds in, and you take these pods off, you can cook them, and get more out than it costs to put in. There's many different ways you can look at and reframe how energy is being used, and there's many ways. It's like wind energy, ocean energy. The oceans are always going to be moving. Hydroelectric is a constant input. We don't need somebody in the ocean trying to make waves. So everybody jump now, make a wave together. No, it's just the tides that come and go, right? And the waves is the wind on the surface, but the depth, though the tide coming in because of the moon and all that is energy input into a system, right? This is where the extra energy comes from in these things. I talked about a quantum mechanical effect in my videos for Exploratory Minds project once. Had to do with geometry, and at the smallest equilateral geometry, at the smallest inward scale, inward pressure, coming up with this. The opposite geometry would be spherical for things that come in outward expansive. And you know, all that bigger picture with that definitely equates to if every point in space and time is infinitely connected to all other points because it came from this one dense, super dense point. Theoretically, everything's zero level energy, 0 point energy, which is a thing. But that got clouded into conspiracy nutty stuff where soon, and now because of that, sometimes when people say 0 point energy, people are like, oh, that don't exist. It does exist. Is there a gas or a given system, or let's say gas, a particular gas that will not freeze? Why not? Because its lowest energetic value stops it from freezing. Right? Everything has its zero, its lowest point of energetic value. A vibrational value, if you will, at the smaller scale, like atoms will spin a particular way, and subatomic particles of that move in a particular way. You just keep on dividing until you got quantum mechanical particles, whatever. I say quantum mechanical because, you know, if you look at the Casimir effect, that is a quantum mechanical effect, where energy can seemingly, it seems like it, but it's not like it. It's seemingly energy coming out of nothing, coming out of nowhere. And what they did was to see if there was energy within a vacuum, like residual energy here and there. And they milled these tiny, tiny plates, microns apart. And these plates in that vacuum on their own, seemingly on their own, slammed together, creating a energetic response, a side effect from that banging together. What pushed them together? Well, the fact that there was more density of the residual energy around these plates than there was room for between the plates. So it was like a vacuum effect, in a vacuum. Essentially, like when it's hard to open a jar, it's because there's more air pressure on the outside than there is on the inside. So the whole weight of that is on that jar, right? And that's kind of a same thing. It's a quantum mechanical effect. That's a 0 point energy thing. That's what that is. The Casimir effect, if you look at the literature about it, though, it was you talk about it being renormalized. It's a terminology. If it wasn't for a certain equation to renormalize what would formerly be recognized as infinite energy, or just so big it's uncountable, right? So I understand that. If you're a mathematician, you want a countable number, because we don't live forever, and we don't have forever, and you're not going to do too much productively forever if you're counting a number forever just to see how much it is, right? But it's interesting. It would formally equate to something infinite, and where's the energy coming from? It's coming from that infinite connectivity. Is the theory behind that between all points? If one point of something, a gas or whatever, has its 0 point energy, then something, and it's connected with other things at the subatomic level, entangled, non-locality, we get into non-locality with subatomic, with quantum mechanics as well, and entanglement, this and that. It's very opposite to the larger macro scale where things appear to be their own thing, separate. But in quantum entanglement, there's no side effect from distance. You get a particle that's entangled with another, quantum entangled, and you could change one, and the other changes as if it's the same thing, experiences a change. And distance between those doesn't matter. I mean, if we could do that on more and more particles all the way up to the macro scale, you got faster and light, you got instantaneous communication, perhaps, across the universe. Wow. But, that's going way off the beaten track. Is even any of that possible, whatever. But you get where I'm going. Understand some of that is over unity is a thing because of this. The energy is coming from that. It seems like over unity. It seems like magic. I mean, back in the Dark Ages, if somebody from the Dark Ages was brought to our time today, this is an entirely different planet to them, a different reality. We're all like witches and wizards. We have these tiny devices with people's faces on them, and people are inside them, walking around. That's how they would see it, right? There's a voice in a box coming out of it. They think somebody was trapped in there somehow, like witchery, wizardry, and evil. Just a handheld torch should be like magic to them. Yeah? Crazy, right? Trying those same noodles again, by the way, as I did the previous video. So, that first paragraph I read to you, to name a few, a recap on that. There are many stumbling blocks on the racetrack nuclear fusion, the reaction at the core of the sun that combines atoms to make energy, generating more energy than it takes to power the reactors, developing reactor-proof building materials, keeping the reactor free from impurities and restraining that fuel within it, to name a few. And there's comma after comma there, these like separate different things. Now, researchers from Princeton University and its Princeton Plasma Physics Laboratory have developed an AI model that could solve that last problem. This model predicts and then figures out how to avoid plasma becoming unstable. If it becomes unstable, you're losing the energy as it got degrading, right? A trophy. And escaping the strong magnetic fields that hold it inside certain donut-shaped reactors. They published their findings Wednesday in the journal Nature. Donut-shaped tokamak reactors rely on magnets to squeeze plasma particles close together and keep them constantly spinning around a ring, creating a lasting fusion reaction. They're one of the front runners in designs for a practical fusion reactor. But if there's one little disruption to the magnetic field lines running through the plasma, the delicate balance keeping it all contained gets out of whack. The plasma escapes the magnets, clutches, and the reaction ends. So it's very difficult to maintain, right? I hope you don't mind me having some noodles right now. So you get the idea, right? Spicy, spicy. Some Chinese person, can't pronounce it, is Qijing Zhao? Qijing Zhao? Don't know. I'll put a link for you underneath. A plasma physicist at the University of Saskatchewan, who wasn't involved in the study, explained that these instabilities can lead to catastrophic consequences. When the plasma stops operating, there are several risks. One is that the energy stored in the plasma is going to be released as thermal energy, heat, and may damage the wall of the reactor. Good point. Yeah, you don't want to damage. It's not very expensive, right? She said, more importantly, a sudden change in magnetic current can introduce a great deal of force on the reactor that can really destroy the device. She also added, I'm not going to pronounce the name, she added, because English being my first language, I'm not very good at reading Chinese names. She added that one of the biggest tokamak reactors around today, ITER, that's I-T-E-R, all in capitals, must be an acronym, in France is only designed to withstand a few of these plasma disruptions. All right. Sorry, but it is fairly tasty. So it's only designed to handle a few of them, so you don't want to risk too many, right? And so this is a problem financially. A few of these disruptions before the whole machine has to be repaired, a huge expense. The goal is to catch instabilities while they're still small and intervene, nip it in the bud before it gets too bad. Unlike the UK at the moment, for too long actually. That'll be a separate video. There's plenty that we're doing this, like we let things get too bad and then it's too much has to be done all at once and it was too little too late. Princeton's lab model can predict so-called terrain mode instabilities 300 milliseconds before they happen. That's a very tiny amount of time before it happens. Micro is just ridiculously small and was imperceptible really, but the technology can perceive it. Human nature can't perceive milliseconds. 300 milliseconds. How many? Maybe I'm wrong. How many milliseconds in a split second? I don't know. This is a very small amount of time, right? I'll see if I can investigate the answer to that question a bit later. It doesn't sound like a lot of heads up. But it's enough time to get the plasma under control. And anyway, how many milliseconds in a split second? Is it a million? Because that's a million per. You see, the term split second is one of those indeterminate phrases and means anything from an instant length to 999 milliseconds, just under 1 second. Yeah, it's about, so there's 1,000 milliseconds to a second. Then okay, I think just roughly looking at that, not much of a heads up. Researchers tested the algorithm on a real reactor, the D111 or D3. It's D and I, or Roman numeral things, and hyphen D. National Fusion Facility in San Diego. They saw that the AI system could control the power being pumped into the reactor and the shape of the plasma to keep it swirling, to keep the swirling particles in check. Co-author, what do you always have unpronounceable names? The co-author person said in a statement that the success of the AI model comes from the fact that it was trained on real data from previous fusion experiments, rather than theoretical physics. That's a very good point. Can we stop feeding AI dysfunctional aspects of human nature? Because facts don't care about our feelings, right? Yeah. And it's where some AI systems appear to be very dumb at the moment. It's getting dumber because it's reflecting the dumbing down of society. Why is society dumbing down? We keep passing it over to a computer to do. Whereas this, a bit different. Yeah. So it's trained on real data. We don't teach the reinforcement learning model all of the complex physics of fusion reaction. We don't teach the reinforcement learning model all of the complex physics of a fusion reaction. It's a convoluted sentence to me. I think they just written down as a person's talking. What the goal is to maintain a high-powered reaction, to avoid a tearing mode instability and knobs. Yeah, it is just. It's a person talking, right? And they're quoting them, right? Okay. The study is significant, said co-author. Another co-author with unpronounceable name, because previous studies have only been able to suppress tearing instabilities after they have happened. Our approach allows us to predict and avoid these instabilities before they even appear. But tearing mode instabilities are just one of the ways plasma can become unhinged. There are dozens of ways a glob of plasma can wobble, bend, or break apart in a kinked garden hose, a fan, or even a sausage. Okay, that's metaphoric, I guess. Nevertheless, tearing instabilities, these instabilities would happen via quantum fluctuations, I guess. Like before they nip that in the bud before it's actually a physical thing. But how do you do that? I might be overly assuming there, though. This reads on a bit more. But there's an article, is that Vice reporting that, and there's, if I get the right page, Quantum tunneling is an essential phenomenon for nuclear fusion. Very important, quantum tunneling. The layman terms of that we go to, in physics, quantum tunneling, barrier penetration, or simply tunneling, is a quantum mechanical phenomena in which a object such as an electron or atom passes through a potential energy barrier that, according to classical mechanics, should not be passable. So you're losing energy and so on from a system. This is relates to these tears probably that they're talking about, and instabilities, to stop too much of the tunneling happening and contain this and keep it stable, right? Is a quantum tunnel a wormhole? Probably. I think so. Getting from point A to point B. Not in time and space, but through it. Through physics. AI will play a large role in controlling and maintaining fusion reactions. According to the physicist at the Swiss Federal Institute of Technology, who wasn't involved in the study, told Live Science, there's a huge potential to unleash AI to get barrier control and to figure out how to operate such devices in a more effective way. They're talking about it as a barrier control. Again, quantum tunneling, barrier penetration. We need the right barrier to contain this, to stop it tunneling out of this. On quantum scale, that would, you get more, the more you got the leaks, it seems like an obvious eventual larger effect. It's a runaway effect of quantum imperceptible, then all the way up to the macro, then you've lost all, if it's a thing that once it starts happening becomes unstable and this produces a exponential reaction going all the way up, and you've lost your energy or it's released as heat and so on. But quantum fluctuations within a vacuum produce a result from the Casimir effect that, for all intents and purposes, was infinite energy if they didn't put an equation in there to correct the number. They needed a countable number, really, I guess. I talked about, I did some videos on a number of things, and that was part of the whole sort of point I was trying to make. The quantum Casimir experiment, the quantum effect, was in those videos. I'm not a physicist. I've had a physicist tell me that I'm on the right track, but they were theoretical rather than actual. Don't know, I just play with this. It's a wonderful thought experiment to look into some of these things. Is what I did with Exploratory Minds when I did some videos on that. And again, if we go Casimir experiment, look that up. Casimir. They theorized the Casimir experiment if there was residual energy within a vacuum. They found a lot more than residual, right? The Casimir effect is always known as. And it was theorized, and they waited till they had the technology to be able to test it. So it was it was much later that they was able to do this. In quantum field theory, the Casimir effect, or Casimir force, is a physical force acting on the macroscopic boundaries of a confined space, which arises from the quantum fluctuations of a field. It is named after the Dutch physicist Hendrik Casimir. Who predicted the effect for electromagnetic systems in 1948. The same year, Casimir, together with Dirk Polder, described a similar effect experienced by a neutral atom in the vicinity of a macroscale interface, which is called the Casimir-Polder force. The result is a generalization of the London van der Waals force. You want to look that up? It's just look it up. It includes retardation due to the finite speed of light, fundamental principles leading to the London van der Waals force, Casimir force, and the Casimir-Polder force can be formulated on the same footing. There was something here. I can't remember where it was, but again, it was predicted with the effect in systems in 1948. It was 1948. They theorized, and when they actually did it, I forget what year that was. Yeah. Casimir predicted and proven. What year? (1948). First predicted over 50 years ago. It seems like energy from nothing, from a vacuum, right? But obviously, a vacuum is not empty. And the videos I did was theorizing that the vacuum is quite the opposite. It's actually infinitely dense. And you think, oh, it doesn't feel dense. Good point. There was explanations for that as well. And if you look at the math, they say, I don't say it, they say infinite energy came out, or a number that would be formally infinite if not for the what they called renormalization, the needed accountable number, right? Space is a vacuum, but a vacuum is infinitely dense. What comes out of space? What's in space? What is absolutely everywhere? So, what is everywhere? Space, right? Even an atom is like 99.9 repeating empty space. I don't think it's that empty. The things come out of it, express themselves on the outward somehow. Ironically, matter being less dense than space is coming out of. Yeah, if you're lost, right, it's so am I. But it seems to go that direction. But these are some of the reasons why quantum mechanics are going to lose us as well. Oh, spicy. But thanks for watching anyway. I don't know what you think, and if you are a physicist or whatever, theoretical or otherwise, I'd love to hear from you. I'd love to have a comment below here and he'd probably hear from you and go, "You're completely wrong. You ain't got a damn clue." But tell me why. Layman term this. Right? Because every time I read about quantum entanglement and these things, I keep coming back to space not being very empty at all. It's so full of energy, it's infinitely full. How does it get infinitely full? Again, everything has its vibrational 0 point value energetically. But if everything is infinitely connected, infinitely, perhaps even infinitely somehow entangled with everything else, quantum entangled, and there's certain types of quantum entanglement, if done deliberately under experiments or whatever, make it more obvious about because that's what we're observing. But then it equates to, that infinite connectivity equates to everything in every single point in space and time has all the energy for the whole universe. This leads to hollow fractal universe theories, like a fractal, all information of the whole fractal. If you look at Benoit Mandelbrot, the maverick mathematician, stuttering, yeah, a maverick mathematician looked into this, and basically, mathematically, it showed that the fractal geometry exists in nature a lot, self-similarity on many, many different scales, and basically they printed images based on that kind of math that you could take a piece of the image and it was a copy of the whole thing. They could zoom in and take another piece and it was like the whole thing again, right? Whereas a hollow fractal universe is like, takes the aspect of holograms. If you ever had, I don't know if you ever bought a hologram out of a gift shop, and if you accidentally broke it, shattered, that shattered piece would have not a piece of the image, but the whole image in that piece. You could break that piece and the whole image is in there again. It's copy and a copy and a copy. Isn't that interesting? Have I gone nuts? No. This is stuff that's occupied my brain for years. And it makes me sound absolutely fucking crazy talking about it. And I might be. I don't know. Thanks for watching. Bye bye.